Hello, everyone. My name is Andrew Ross. I'm going to talk about some work I've done evaluating machine learning parameterizations of ocean subgrid forcing, which is joint work with Lorzana at Courant. So turbulence, unfortunately, is hard. And even though we have basically the right equations of motion for a lot of what's happening in the ocean, we can't simulate it at high resolutions given current computational limits, or at least we can't usually. There have been some simulations that have been run at great cost at pretty high resolutions. And we see that when we actually do increase those resolutions, critical predictions in climate models often change. For example, the prediction of maximum sea level in the Northeast US is about 50 centimeters higher in this high resolution run. So that might be important. And sort of the typical strategy for dealing with this problem, or at least one that's received a lot of attention, is running models at low resolution, but finding some way of parameterizing what we're missing. Now, the way that we actually sort of, so one approach that's been pretty common recently to try to learn subgrid parameterizations is to use machine learning. It's also common even in sort of traditional subgrid parameterization research. So what we do is we try to quantify what we're missing at the coarse-grained level by starting with some high-resolution initial state. And in one case, sort of the top branch, passing it through the equations of motion to get a tendency, and then filtering and coarse-graining that tendency. But in the lower branch, filtering and coarse-graining first, and then passing it through the equations of motion. The difference between these two tendency terms quantifies the error that we have accrued due to the lower resolution. And so the typical workflow in a machine learning sort of approach to this would be to generate a big data set of a lot of initial states and a lot of corresponding subgrid forcings, train a machine learning model to predict SQ from Q or maybe other factors as well, and then evaluate performance in some way. Often this is just sort of offline performance where we measure how well we can predict SQ from other initial states. We do also, we all agree it's important to evaluate these online, but it's often harder to do that because these are big climate models sometimes. But in any case, there are few ambiguities that I'm sure that all of us have encountered who have worked on this. So there are actually many different ways of filtering and coarse graining your high resolution states or your tendencies. I guess you could do a different method for each version. And those lead to very different forcings. You can also use different numerical methods to compute the forcing. And you can do it often in terms of different state variables. So you can compute the forcing in some simulations with regard to velocity or potential vorticity or other sort of variables, which sort of may redundantly encode the same state. And you can use those different state variables as inputs as well to the machine learning model. And I mean, everyone knows that offline performance is not the same as online performance, but they can often be very different, as we'll see in this talk. And also there are many different ways of quantifying performance. So we're going to sort of investigate a lot of these questions in this talk. But to start off with, we're going to introduce a sort of simulation environment that allows us to run parameterizations online. So that's PyQG. It's an open source library. We're going to sort of run it in a two-layer quasi-geostrophic mode, which solves these equations. We can make nice plots like this. So we're going to mostly focus on configuration settings that produce flows like this. We also test transfer performance. We won't go into that in this talk due to time. And we can see that when we run it in high resolution, which is the grid, which we define as grid size, sort of larger than twice the deformation radius, we get sort of convergence. But when we start running it at lower resolutions, we start to see divergences in many quantities, such as the kinetic energy spectrum. Okay, so let's start to sort of go through the things we're going to study varying. So we're going to try 3 different ways of filtering and coarse graining our high resolution states. So 2 versions, which are spectral filters, which makes sense because PyQG is sort of a pseudo spectral model, and 1 version that operates in real space using the GCM filters library. We're also going to compute the subgrid forcing in different ways. We're going to compute it both in terms of potential vorticity and velocity, which we can convert back to PV using the curl. And we're going to do that using the traditional advection equation. We can also do it in sort of a flux formulation where we predict two quantities whose divergence is equal to this, to approximately equal to the subgrid forcing. And then we can also do an empirical version where we don't use this advection equation, which requires computing derivatives outside the model, but we actually pass it through the model, which includes some extra differences in how high-res and low-res dissipation work. But in any case, we're going to vary those 5 different options as well as these 3 different filters. And we're also going to vary the inputs. So we have 7 possible inputs from the power set of Q, U, and the gradient of U, which is often used as an input because it sort of is a little less sort of specific to the flow than U sometimes. And so we vary the inputs, we vary the filtering scheme, and we vary the forcing formulation. So we're going to study the effects of doing that. And because that is already 100 plus combinations, we're going to only consider one neural network architecture, which is fully convolutional neural networks that have sort of proven effective. We're going to also use physical constraints and sort of periodic padding to ensure that we have 0 spatial mean for our predictions of forcing. And we're going to run these parameterizations online and compute many, many realism metrics. All right, so the metrics is sort of where a lot of the meat of the contribution is coming. So we're going to introduce 4 types of metrics. The first is sort of computing sort of curves like the energy budget terms. So there are 4 of these after running the simulation. These are time averaged, running a simulation online. And we just compute the mean squared error between 2 curves. So this illustrates the difference between the high-res curve and the low-res curve and the difference in red. We can also, other quantities we want to sort of visualize in log space and take a sort of best fit slope over the sort of set of wave numbers or scales that are inertial. So we can do that again with the high res and low res, and we see that they have different slopes, again, visualized in red, the difference. We can also look at the quantities at the end of the simulation, kind of flatten them spatially, and just look at differences in the distributions between these quantities. This might correspond to like differences in the distribution of sea level in a more realistic simulation. And then you want to quantify some distance between those 2 distributions. In this case, we're using Earth movers distance, which is sort of pretty nice for dealing with sort of physical quantities where you don't just care about whether they overlap, but you also care about sort of how much mass you need to move from one to get to the other. And finally, a slightly different metric is we look at the time it takes for 2 simulations to diverge from the same initial conditions. If we're sort of operating with 2 high-res models from the same initial conditions with a small perturbation, it takes them about a year to reach below a threshold correlation, in this case 0.25. But if we look at a low-res versus a high-res model, obviously we have to compare the correlation after filtering and coarsening, but they only stay in sync for about 2 months or a little less. So that's a significant difference. We would like to we would hope that a parameterization keeps the state in sync at least a little bit longer. Obviously chaos is still a thing. Anyway, so those are our distance metrics. That actually gives us, I think, 17 different distance metrics. But to help interpret these, one thing we can do is we can convert these metrics to a similarity score if we pick some sort of baseline and a target. So in this case, the target we're going to say is the high-res simulation. We want the parameterized simulation to resemble the high-res simulation. And we can sort of look at the distance between that simulation and the high-res and compare it to the distance between the high-res and the low-res. So we can, this formulation gives us a similarity score that quantifies what percentage we are closer to the high-res than the low-res. So in this case, we can see this parameterization, which is in green, which does pretty well. And the similarity score is 0.86, meaning we're pretty close to 1, which is sort of the ideal. The Smagorinsky parameterization in this case, which is a baseline, is negative. It's doing worse than low res. And of course, high res is 1 by construction and low res is 0 by construction. Great. So yeah, we have, between all our models and all our scores, we've got 2,000 similarity scores. I had a hard time figuring out how to parse through this and figure out a nice way to visualize it. We could look at the top parameterizations by different categories of metric. I've done that here and sort of, yeah, some of the models do really well. You can see the KE, like for this dotted red model, is really close to the high res in orange, and all the energy budget terms match up well, there are differences here, but I think it's more interesting to sort of try to figure out the overall effect of each design choice. So we're going to have a different visualization here. So we're going to take these energy budget comparisons. We're going to take a median and aggregate them by condition. So this is going to show you a distribution. We're gonna do a probability distribution of our own results here now, rather than the physical quantities. And so we're going to look at the similarity scores that we get for different design choices. So in this case, we're looking at the similarity scores we get for distributional similarity. I think I have the label here wrong. Sorry about that. And it looks like using a sharp spectral filter gave us similarity scores that were consistently sort of even above 0.5. And that's a lot better than the real filter or the soft spectral filter. Additionally, it seems like sort of expressing our forcing in terms of velocity rather than potential vorticity tended to do a little bit better marginally, or a decent amount better actually. And also, so the input mattered less. You can see there's less distinction between these curves than for filter or for forcing formulation, but it looks like using just straight up velocity rather than sort of all of the features, which is in green, that tended to do a little bit better online. And we get similar results for, again, energy budget similarity and the decorrelation time similarity. You can see why I confused them because they look so similar. The effects are a little less pronounced for sort of the decorrelation time similarity, but basically sharp spectral filter did best, velocity forcing did best, and just straight up velocity did a little bit better. Now, if we look at other metrics, such as the slope similarity, the similarity in the log-log fits of the slope, and also offline R squared, which is sort of the elephant in the room here, we get pretty different results. So in this case, a real space filter led to more similar spectral slopes. Velocity forcing still did best in terms of spectral slopes. The input made less of a difference, but when we go to R squared, the filter that did the worst by the other metrics does the best. Maybe because the underlying problem is a little easier, but the problem we're solving no longer corresponds to the problem that leads to the most similar predictions to the high-res model. And also, the sort of flux formulations did better, which is interesting. You know, they didn't make much of a difference. It was mostly velocity versus PV, but that's interesting. Maybe it's easier to get higher R squared. And of course, we see here that using all the inputs gives us better R squared rather than the fewest inputs. But that does worse online. So hopefully this illustrates how using offline performance can be a little misleading sometimes in sort of looking at online performance. We can also visualize this by looking at sort of the correlations between the rankings you get if you rank all the models by sort of the median score in each group of metrics. And you know, this is sort of repeating the same thing, but we can see that the rankings we get when we sort of rank models by distributional, energy budget, and decorrelation time similarity are all relatively similar, while the offline R squared and spectral slope rankings are a little less correlated, especially offline R squared. Great. So we computed lots and lots of metrics for lots and lots of parameterizations. We looked at sort of distributional similarity, similarity in the curves of the energy budget, similarity in the slopes of different energy and entropy spectra, and also how long it takes two simulations to diverge from essentially the same initial conditions. We found that all of our design choices actually mattered, though to different extents. The filtering scheme mattered the most. The forcing formulation also mattered. The input mattered a little bit. But of course, there are still ambiguities here. You know, we defined all our similarity scores by picking the high-res model as the target. Now, if you picked instead some sort of filtered and coarsened high-res model, perhaps filtered and coarsened with a particular filtering scheme, then it turns out that the models trained with data generated for the corresponding filtering scheme are the ones that tend to do the best. So we shouldn't sort of poo-poo the soft spectral filter completely here. I think this points to a larger question of, you know, when you're designing evaluation methods and you don't have a firm ground truth, it's hard to evaluate your evaluation methods. But in any case, we have, as part of this project, we've updated the PyQG model to support parameterizations. So that's now available on the master branch. We hope to open source more of these sort of tools and toolboxes soon. So look out for that. And yeah, happy to take questions. Thanks so much.